through the river, through this ancient city, goes a river. Like all great civilizations, it's remarkable that most civilizations are founded next to large water bodies, to rivers, to oceans, to lakes, and so forth. Well, Chicago is next to Lake Michigan, I suppose, and so on and so forth. Right? We all live next to the sea. So this ancient city is next to a famous river that in the West we call the Ganges, and in India we just call Ganga. And many of you obviously have visited it or had a dip in it and so forth. It's considered of great relevance. So this particular city has houses, let us say, houses. I'll just mark the houses with a triangle. On one side of the river, on the river bank. In fact, if you Google up any picture of Banaras, you'll see something quite remarkable. One side is absolutely densely populated with houses. They are called the ghats. The one side, this side is the ghat, right? And densely populated with a lot of buildings. And even back down, it is all buildings, 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 and more buildings. So it's just this area, you can say, roughly speaking, is like a non-agricultural, like they are housing of some form, housing or commercial or something like that. Everything is here. People live here. In other words, this side is the, oh, let me use a more appropriate term. This side is the population center. On the other hand, remarkably, as you can imagine, population center tend to be expensive real estate. Right? That's the lesson we learned from the California housing in our last lab. And of course, we know it from practical experience. On the other side, you find trees and just plain land and agriculture. So I'll just draw some trees, but actually not even trees, they're shrubs or just fields, agriculture, re-culture. This side is agriculture, culture, and terrible spelling, but okay, agriculture. And this forms the context of our setting the stage for understanding SVMs. So the problem statement is this. If you pick a geographical point X, right? So this is your X1 and X2, let us say. You pick some point, and let us say that you pick a point either here, here, here. You need to determine what is it? Is it a population center, or is it agriculture land? Or are you in the middle of the river? Right. So that is the, so does it look like a classification problem, guys? We'll treat it as a binary classifier. We'll say, can I build a house here or do I grow food here? The question is, or build or find a house here, or is it agricultural land? That is a question. So it's a binary question. Huh? So we are going to classify between house and agriculture. This is our target space, isn't it? Let me write it in the way that we write. The categorical variable, the space is made up of house, agri, these two things. And we have to create a classifier that will take, given X, we have to do a classifier fx that will take you to either a house or an agricultural land. So does this look like a typical classification problem, guys?
Yes.
Right? Yeah.
Yes.
Yeah. So by the way, there's a little bit of a curiosity as a physicist, this may invite you, that it is a remarkable fact that if you look at rivers throughout history, you always find civilization or population centers only on one side of the river, not on the other. Well, things have changed. For example, if you go to the River Thames in London, right? You do notice that there are embankments now, and there's equal population centers on both sides, right? So the river seems to be going through a population center. But without those human engineering efforts, if you look traditionally as how rivers have been and civilizations have related to it, you always find population centers on one side and agriculture on the other, or your plain land on the other. Now, I'll pose you guys a puzzle. Why do you think this is true? It has nothing to do with machine learning, by the way. But I don't know if you ever observed it while you're traveling throughout the world, that population centers tend to be on only one side of the river. Unless it has.
Asif, I think one of the reason is like the floods. Yeah, because I live on the other side, like on the flood side.
Yes. So, but why are the floods there on one side but not the other?
I think it's because of the gradient or the way the water flows.
Gradient is there. So one side is steep, the side of the population center will be steep. On the side of the agriculture, it will be gentle slope, right? And the water easily rises up the slope. But why do rivers behave this way? One bank of a river is steep, other bank has a gradient, slow slope, and so tends to get flooded more.
The rotation of the
erosion over time.
Come again?
Erosion over time.
Erosion over time, sort of, yes, it is part of the answer. Okay,
The rotation.
rotation.
What direction it erodes?
Yeah, rotation of what?
Earth.
You're getting very close. Rotation of the Earth. So why does it erode in one direction? Actually, so I'll give you the answer. It's very beautiful, actually. There is a force in the force that is created, a form of a centrifugal force. It is called Coriolis Force. It's the Coriolis forces cause the rivers always to drift one way in the northern hemisphere. Have you noticed that most rivers tend to go from northwest to southeast in the northern hemisphere quite often, right? Or as they move, the rivers also drift. They never remain at the same place. They move over the hundreds of years. Now, the way they drift in such a way that they have actually drifted in this direction. So when they drift in this direction, ultimately you have the embankment, but the place that they have left used to be the bottom of the river. And that is first very fertile, and secondly has a gentle slope. Right? Which is why one side is just alluvial soil. For example, on this river, it's fertile alluvial soil, and you can do a lot of agriculture. So anyway, for the physicists amongst you, this was fun. So today I'm taking obviously a long-winded way back to our main topic, lots of digressions. That's what happens when your instructor is fond of the topic, lots of digressions. So all right, we'll come to that. So now the question is, once again, let's get back to our river. Suppose your river runs like this, and I'll pose the problem like this. Imagine that it is pitch black, because that's how a machine learning algorithm sees it, x1, x2, right? You have to find a decision boundary so that you can say one side is our houses and another side is agricultural, is trees. Let's use the word trees, even though it wouldn't be trees, it would be shrubs or agriculture. How would you do that? You would say that, I am looking for the median of the river, the middle path in the river, right? A river is here. This is what I'm searching for. So now let's try to do that. Suppose you have houses like this and a tree like this, something like this. So think in how many ways you can flow a river. You can flow a river, for example, like this, and you see that it still fulfills your criteria. The green river, isn't it, guys? You could flow a red river because you can't see the river. You could also have flown a river like this. Now, between the white river, let me give these names to the river. This is A. Let's say this is B river, and the white river is the C river. right? From a data perspective, which of these seems more convincing to you? If you had a,
White.
C.
you would say why? Because you suspect that if you have seen this data, there is likely to be a tree here that is not there in the data, isn't it? And likely to be a house here. You can sort of extrapolate and convince yourself that these narrow rivers that you can flow probably are unstable solutions. You take a different sample of the data and you would be able to flow a different river through it, isn't it? So if you had to choose which river is the best to pick, which is the best river you can flow through your data between the houses and the agriculture, your best river would be, what characteristic would it have? What does C have compared to A and B?
Broad.
Is wide, isn't it? Is the broadest, is the widest river that you can flow through your data. Are we together? Right? The basic intuition is if you want to be robust, take the widest river that you can flow through the data. So that is our first intuition, right? And this is how these ideas develop. So let us write it in formal terms. We want to flow the river through the data, isn't it? This is our intuition. Intuition to have a stable or good solution. Is that right, guys? Is this intuitively obvious what I'm saying? So ponder over it for a moment and see, would you agree with that intuition? Any questions? Is it more or less obvious? I hope so. Huh? So this, well, you don't, in machine learning, you wouldn't be taken too seriously if you say in a professional environment that I'm trying to flow a wide river through the data. So it needs a more technical or sort of a more mathsy formal language. And the formal language you say, you want to draw, you are searching for, so these banks of the river are, you are searching for the maximal margin. Actually, let me write it in capital because it's a term that you should remember. Maximal margin hyperplanes. So this river, this bank of the river, let me just call it bank of the river one. Bank one of the river. And this would be, this thing would be bank two of the river. So a river has two banks. Right? So these are the two banks of the river. So you call them, a bank is a hyperplane. Well, in our case, it is just a line, right? But a line is, is a hyperplane using more formal language, because in higher dimensions, that's what it would be, hyperplane. So far, so good, guys? So do you see how this translates to this? You are searching for those river banks that gives you the widest rivers, right? A widest river to flow through the data. Any questions so far? And then the decision boundary, is simply the median hyperplane, median path or hyperplane between the two riverbanks, or if you want to use formal language, is basically the path. So if you think of yourself as a boatman, a little boat, so one intuition that I can think of is imagine that you're this little guy on the boat and you're rowing. So you want to hit neither the tree nor the houses. Late at night, you don't want to get stuck either on this side or this side. What path will you take? The path that the boatman will row is the decision boundary. Is it looking simple and intuitive, guys, so far? So when you do that, what we have done is we have taken the first great milestone on our journey of understanding support vector machines. This particular algorithm is called, literally by its name, maximal margin classifier. I hope the name is suggestive of what it tries to do. What does the maximal margin classifier try to do? It searches for the two hyperplanes that enclose a river as wide as possible through the data. Clear intuition, guys? Right. Now, here is the thing. Sometimes people confuse and say this algorithm is support vector machines. No. It is the first step in the journey towards support vector machines. But it is gets a little bit more complicated. These houses that help, that are hugging and the trees that are hugging the hyperplanes, so the river banks, the houses and trees, banks are called, what are they called? They are called support vectors. Are we together? I like to imagine, think of them as lighthouses, houses for helping the boatman, the boat, navigate. Right? So in the sea, we have these lighthouses along the coast that give you a sense of how to navigate, get closer to land. In the same way, think of these as lighthouses, except that on a river, or if you go to the city, you will find that there are no real lighthouses. It would be the light shining in people's homes, or what people do in this city is something actually pretty poetic. Every evening in the water, you find this beautiful little earthen lamps made, terracotta, baked clay lamps with lights on them. And this practice of putting these little lamps into the water goes back thousands of years. It is really evocative. Whenever I think of my hometown, the picture of these beautiful lamps in the water comes. So, well, here we go. Think of these as lighthouses or lamps in the water, or lamps in the water edge. Are we together? So do you see that so far the intuition is very clear? If you look at this picture, you realize that if you are in pitch dark and you are a boatsman, and you see, let us say that you see one light here, and you see, let us say that you see another light here, and you see a light here on the other bank of the river, right? You know that this side is agriculture, maybe the agricultural lights are green in color, and these are more like amber in color, right? Or something like that, yellowish in color. I'm just taking distinguishing marks, right? So they stands for houses, house. You know that this is a house, and you know that this is a tree or a shrub. Right? Can you imagine that you're in pitch darkness? What is the river that you can infer as a boatsman? Would you agree that the river that you would infer would be something like, let me take the color of water. The river that you would envisage would be essentially this, isn't it? Where this data point and this data point and this data point are sitting. These are your support vectors, right? How many support vectors? You realize that you just need 3 points to draw your river. And therefore, you need only three data points to draw out your decision boundary. Your decision boundary is simply the path that the boatsman takes, flying through the river. So ponder over it for a moment, guys. Make sure you get the intuition, the geometric intuition here. Is it looking easy so far? Imagine you're in pitch dark and you see this, maybe I'll color these differently, a yellow light. These are yellow lights. And these are green lights. Do you think that this is enough for you to be able to draw your maximal margin hyperplanes, or simply put, discover the banks of the river and then ply your way through the center? A little bit of thought. Anybody who disagrees or thinks this needs clarification? Any thoughts, guys? All right. So if it is clear to all of, Aditya, go ahead. Were you asking something?
Yeah, I was saying, like, if there is a bend in the river, then...
No, so we are going there. It's a very good thought. Hold that in your mind. At this moment, we are looking at a very simple river, a segment of the river, and this is it, a straight part of the river.
Okay.
So but we'll come to the more complicated situation. That's why I said it's a first milestone, right? But in a straight river, this is enough to do that. And so that brings us to some very remarkable conclusions. This algorithm, which color should I use to emphasize the beauty? Maybe I'll use this. This algorithm is robust, and this is something that startles you when you see that it's obvious, robust against outliers, isn't it? So for example, suppose there are houses way out here and there are green things way out here. Do you think they matter, all of these things far away from the decision boundary? Do they really matter? They don't matter, isn't it? This house and this tree, they do not influence these outliers, right? As we can see, outliers are almost irrelevant, or practically irrelevant, terrible, relevant to the discovery, to the learning of the river path. In fact, it is the inline data that matters most. That is one startling observation. The other startling observation that you have is the model after that becomes so simple. Do you realize it is a shockingly simple model? It is a shockingly model. Just a list of support vectors. So let's explain this word, support vectors. See, this is a point of data. This is a point in the feature space, isn't it, guys? So suppose I put a coordinate system here, x1, x2. You would agree that this represents a point. This represents point x, let me just call it xa, a vector. This represents a point xb vector, and this represents a point xc vector, right? Every point in a Cartesian space is just a vector, isn't it? Can be written as vectors. So the word vector is therefore understood in this context. The next question is, what about support? You're saying that you need only 3 vectors to support your decision to flow the river like this, isn't it? Your decision boundary is supported or proven with just these 3 vectors, just a very small list of support vectors. So you may have a data set that has thousands and thousands or tens of thousands of points, but your support vectors may be a very small list of a handful of points along the riverbank.
Asif,
Yes.
if your green support vector was an actual outlier,
You mean this one? No, you're not an outlier. So the assumption is that around the green point, there are lots of other green points.
right, Asif. But if it's very far out, let's say
Yeah, that is an outlier. Yeah, it is. See, outlier is invariant of the classifier you use, right? Outliers are outliers. And you can discover outliers by the usual manner of outlier detection. So detecting outlier is easy. The hard part is that when you have outliers in your data, how do you make your algorithm not be hijacked by outliers? Now, if you remember, for linear methods, outliers were pretty nasty, right? They would screw up the model, and we would do all this outlier search and so forth, and make sure outliers are not there. But one nice thing about support vector machines is they are very robust against outliers. They couldn't care less because they are searching or not being influenced by outliers. They're rejecting the outliers. They're actually searching for those high value inline points, A, B, C, right? That will help them support their decision boundary. And points are vectors in Cartesian space, and thus the word support vectors. Do you see that, guys? Right? So what we just
Asif,
learned, go ahead.
Asif, just one question. So that the boatman rowing there, so that's the decision boundary, right? Now, if let us say pick a point between that line which the boatman is rowing and that other blue line, the one on the right,
Yes.
that is still not the, what is that called, the green area. It is in the river. So how do we avoid that problem?
No, so let me try to parse what you said. So there are 2 river banks, right? This is the bank, let me say to the left and to the right.
Yeah.
And the boat has discovered what the 2 is. So what it will do is it will first draw this line. To draw a line, you need 2 points in a Cartesian space, isn't it?
Yeah.
Or a hyperplane, you need these 2 points. You drew the first line. Now you have, okay, yeah, this is an important thing I should mention. The other plane has to be parallel to this. So what will you do? You will start with drawing little planes parallel to this and see how far you can go till you hit a green tree. And then you'll stop, right? So you will stop here. The first green tree you make, you stop expanding your river and you say, now I need to stop because now I've hit land, isn't it? And so the boat can see that, and therefore it will draw these 2 big blue lines and it will take a path midway through this, which is the decision boundary.
So, but to decide whether it is a house or a tree,
You're given
it has
that.
to take that whole margin into consideration, not just that line, right?
Yes, it has to take the whole margin. So what it does is, see, this is given data to you, this is training data.
Yeah.
The houses are burning yellow. Let's say the trees are burning green. The light in the trees is green, let us say. And so they are well there. You're trying to learn from the data. So you're trying to flow the widest river you can through this data. Okay. So how do you do that? Learning is always an iterative process. You flow a river through the data, and then you try to make the river optimal, the widest possible. So that is the implementation of the support vector machines. And support vector machines, when they came out, they were notoriously expensive to implement computationally. So the theory is very simple, but when you try to implement it, it gets rather intensive computation, because in a plane, you can imagine so many rivers that you can flow through it. For example, you could have on this from this river. Obviously, that wouldn't have been a good river. It's not the maximum margin hyperplane river, the widest river that you can flow through the data. Are we together, guys? Abhijit, you got that? Is your question answered, Abhijit? You're on mute.
Yeah.
No, it's answered.
Yeah.
Okay. So guys, let us recap what we learned, because this is a foundation. First of all, the intuition is we want to flow the widest river we can through the data, because that would be a good solution. It would be, it would have low variance. In other words, if I take a different sample of the data, I shouldn't end up with a different river. And for that, try to find the widest. So more technically, so in my mind, whenever I think of support vector machines, I always think of river and the widest river you can flow. But that's not that is a language unique to me. So don't open a textbook and expect words like river and river banks. They will use more formal terms. They'll talk about maximal margin hyperplanes, and the decision boundary will be the path of the boatsman. Right? That's how they call it. So this classifier is called maximal margin classifier. It is not the support vector machines algorithm, which is, we're going towards it. But confusingly, these points that help us make the model. So the model is just the collection of points on the riverbank. Those are called support vectors. They are vectors in a Cartesian space, and they support the decision boundary. Right? So that is that. Now, there are two problems that.
I have a question.
Come again?
I have a question. So the support vectors, like 3 support vectors here, right? So, but they belong to 2 different categories of data.
Yes.
Right? And the finding the widest river is basically finding the maximum gap, maximum separator, which separates the data of 2 different categories.
That is true.
Okay. And that's why it is computationally intensive, because we can start with any river, but finding the widest one is the computation.
Yeah, actually the linear part is not that hard. We can quickly get to it. But when I get to the full support vector machines, it gets harder. Even this takes some effort. But as you move forward to the more complicated one, the full support vector machines, then it begins to get hairy, and you'll see why.
Sir, but what if there are, there are multiple categories, like basically multi-class classifier data?
For the time being. So that is one limitation of what I've just explained. I will tell you how support vector machines overcome that. But fundamentally, the theory of support vector machines, very much like logistic regression, is inherently a binary classifier.
Okay.
Right? Blueberries versus grapes and so forth. That kind of a thing. So here, let us think as a binary classifier. So it's good that you mentioned that. And we will see how these things are generalized or harnessed, or any binary classifier can be harnessed to do multi-class classification.
Got it. Thank you, sir.
Okay. So far, so good, guys. Now what we do is, we look at the limitations of it. And there are many limitations. One is that you can only tell between houses and trees. So binary is one aspect of it, but that can be easily addressed. Let's look at more complicated aspect of it. If you have lived next to the river and seen that rivers flood during rainy season, especially in the tropics, and nowadays, well, in the temperate regions also, we know about the floods in Michigan and so forth. So rivers flood, they overflow their banks, and complicated things happen. So then let us say what happens when rivers flood. You find that they drag in, and again I'm giving this narrative to just explain the concepts. So they will wash away a few trees, isn't it, guys? You will see a few trees washed away into the river. So then the question comes, suppose you just see 2 trees here, but most of your trees are here, most of the things are here. What should you do? Would it make sense, and this is a question I'll pose to you, to redraw the decision boundary and say, well, fact of the matter is, I'll use a different color here. Which color should I use? Let's use this color. It's a pretty multicolored thing. And should this become your new river? Do you see this thing? Should this become the new river? I'll pose this question here. And let me ask this question. Oh, this is really multicolored. Should this be the new river bank? Basic intuition says that no, but sometimes you might find a tree or two in the river that is perfectly normal. The river is wider. Its boundary shouldn't be determined by the first tree that you hit upon. Right? In other words, you should allow for mistakes. And this becomes even more apparent if, for example, you realize that this particular green tree could easily have washed its way and come here, right? Gone towards the other side. But then you get into even more problem, because if you try to draw your river, where is that? Draw your river, but now your river is beginning to look rather narrow. Do you see? You're just left with this little bit. And your basic intuition says that this one point, this one tree that has washed into the river has essentially hijacked your model, isn't it? You somehow don't want it to make the decision of where the bank of the river is. Would you like to agree with that? Is that intuition clear? Or would you like to discuss or talk about it?
Yes, sir.
It is clear, right? And those of you, I mean, if you come to, for example, Benares, you see it happens in the rainy season. Anil, isn't it?
Yes.
Of course.
Yes,
And
sir.
right. And actually, there's more complication if you are there. In the cities like in Benares, there is such a thing as a houseboat. What it means is there will be little houses like structures, but they are actually sitting upon a boat, right? So they are triangles sitting in the water. Once again, and this triangle may this guy would have gone to the other side of the. Well, now this picture is getting rather busy. A few of these houseboats are floating around on this or that side of the river. And once again, you don't want just a few of these to make big decisions. Ultimately, this is the population center, and just a few isolated points shouldn't make the decision. So what you do, and by the way, I'm explaining all this without mathematics. We'll go into the mathematics now. So one thing you would agree that perhaps, did I spell that right? I think so. Perhaps we should allow for a few contradictions or mistakes, right? Would you agree that don't make your decision boundary, don't agree on your river banks just because you met one or two points. Meet sufficiently many points before you're sure that you have hit the river bank with the population on it. Likewise, on the other side, meet enough trees before you decide that, okay, now we are talking of the other river bank on the agricultural side. Are we together, guys? We are being more permissive. Otherwise, a river would not be wide enough or would not even exist. For example, with this tree here and this houseboat and this houseboat here, you realize that it's practically impossible to find any decent decision boundary, linear decision boundary, right? You will end up with a no solution situation. Right? So you need to be a bit permissive. So we need permissiveness here, permissive. But then how permissive? It can go a bit too far, right? You keep meeting house after house after house, and you can't just keep saying, no, I'm still not on the bank, I'm still not on the bank. Like, you realize that becomes rather counterproductive. At some point, you have to accept the reality and say, well, now we have hit the river bank. Is that common sense? So we need a certain threshold, right? And to do that, what you do is you set up a cost. You set up a penalty. So the two steps you do is for each mistake, you set up a penalty, epsilon I, right? Suppose it is the ith point, you set up the penalty. And then you put a constraint saying that sum of all penalties has to be the sum. Okay, I use epsilon for, let me use, because the symbols are beginning to look rather surprisingly similar. Epsilon I. The summation over I of the epsilon I, in other words, the sum total of all the penalty, C is equal to this, and constraint that you want to, this is sort of like a cost, total cost of penalties you can afford, right? Cost of penalties. And then you have a budget, then budgeted penalties, then have a budget. Say that you can afford only C greater than or less than equal to some particular value. All right. Let me just say C, well, let me just say, this is typically the word C itself is used. So let me use little c here, little cost, C. This is common. So you can say that your little c has to be the budget. Or why don't I use the word budget? People use the word C in the literature. So I was using C. Let me use the word sum of all penalties, right? Sum of all penalties. So then the sum of all penalties must be little less than your budget. So the language actually in the support vector literature is a bit at divergence with what I say. They will call this C as the cost, right? But intuitively, it is more the budget that your budget for mistakes that you're allowing, so that the sum total of your mistakes or the penalties do not exceed the budget you have, right? So I suppose this is literature. I mean, it's one way of writing it. And I used to find it a little worrying in the beginning when I was trying to teach myself this thing years ago. So we came across our first constraint. We should do this. Cost of penalties is this. And this is in the language of mathematics, you call it a constraint. This is a constraint. Right? And what we are going to do let's take a little break, and then we are going to learn that this entire problem, this entire problem is a classic constrained optimization problem. Constrained optimization problem. By the way, guys, do not be scared with this big, scary words. There's nothing to it. These are very simple, very obvious words. And when we develop the theory, you will realize that actually this is just common sense written out in symbols, and we'll do that. So far, so good. Before we take the break, can we review and make sure that we understand maximal margin hyperplanes? Maximal margin hyperplanes is the search for the widest river that you can flow through the data, or search for those two hyperplanes that will give you maximal separation between the two classes, houses and, let's say, trees. Right? The decision boundary will be the median going between the two hyperplanes, and so is itself a hyperplane. One good quality about the support vector, this maximal margin hyperplanes, is it is really, this class of algorithms is very robust against outliers. Outliers become irrelevant, actually. Very, very nice. The other thing is that's nice is the model is so simple. You just have to tell which are the support vectors that help you, that make the decision boundary, or which vectors or points are vectors. So which points, list of points basically that specify uniquely the decision boundary and the hyperplanes, the river banks. You can say it in whichever manner that you want to, but that's about it. Right? That says the gist of it. Now, the trouble with this kind of a thing is real life situation is data has noise, it has mistakes. And so you don't want to be hijacked by all these mistakes and noises. So you want to keep, you want to define a penalty term for each mistake and then sum all the mistakes and then say that you have a certain budget for mistakes. You should not exceed that budget. Otherwise, your solution will become either very hard to find or very unstable. You take another sample of the data and your river will look a different way. In other words, it wouldn't be wide enough in simple intuition terms. Are we together? So therefore, we have a constraint. All of machine learning problem is an optimization problem in the sense that you take a loss function, you decrease it and so forth. That's a mathematical language in which we encounter all this intuition. So in the, let's take a little break and after that we'll come to that, developing the mathematical language. I said, would you like me to just summarize it again? I will just go back to the previous screen for 1 second and repeat what I said. Let me go there. Yeah. So what I said is that if you have a decision boundary between the blueberries and the cherries, here you see it with this greenish line, then how do you decide if a certain point is representing a cherry or a blueberry? The intuition is that if you take this orthonormal vector W hat, and you say that the further along you are in this direction, based on your distance from the decision boundary, this distance being positive, this distance being negative, based on how far you are from the decision boundary, you can tell whether it's a cherry or a blueberry. Right? A cherry, if you're far, a huge positive distance, very sure there's a blueberry. If it is a huge negative distance on this side, and for small distance, there's a certain degree of uncertainty. So that brings up the usefulness of a distance function. How distant is a point from a decision boundary? So we go through a derivation and we find that the distance function can be represented as this term. It is a dot product of the unit orthonormal vector, W, with the point itself, along with a bias term, W naught. The W naught is actually the negative of the distance from the origin to the hyperplane. So minus the distance needs to be moved to go through the origin. So you have to move minus W naught distance. In other words, in this direction for the hyperplane to now still remain parallel to itself, but go through the origin. That's one way of thinking. But the net result is this: the distance from the hyperplane of a point is given by this term. Two factors are affected: the orthonormal vector of the hyperplane and how far the hyperplane is from the origin. Right. Now, the orthonormal vector, why do we give it in terms of orthonormal vector, a hyperplane's definition, and is distance from the origin? Because it is something that works for higher dimension. For a line, you can go with the slope, but what do you talk about when you have a hyperplane in high dimension? It turns out that you could actually use every hyperplane in whatever dimension has an orthonormal vector, and every hyperplane will be a certain distance from the origin. And these two things uniquely define a hyperplane. Right? So we will take these results, bring it back to our current pursuit, and see how we can quantify all this intuition of flowing a river through the data into a more mathematical language. Are we together, guys? So here we go. So let me bring back that intuition. I'm saying that, let me draw in the same way that it was drawn here. Suppose this is a decision boundary. We are saying that a given point X, and let's say that this is the origin, and from the origin you have the shortest path from the origin to this is This will be, of course, 90 degrees. And this is minus W naught, right? And the unit vector here is W hat, unit vector. Actually, I will use the notation that is in your book. In the book, textbook, they tend to use the word beta naught, beta rather than W. So I'll just omega rather than, so I'll use beta here, unit vector. What is a unit vector? Unit vector is a vector whose size is equal to, what is the magnitude of a unit vector?
1.
Right? So that brings us to our first constraint. It is a constraint on the constraint on the betas, because beta is nothing but beta 1, beta 2, depending upon how many dimensions there are. Suppose there are d dimensions, suppose, let me just say n dimensions, n dimension, then there'll be an orthonormal vector in the n dimensional space where we are talking about, let us say, r to the power, the R Cartesian space of n dimensions, right? And so we came to the conclusion that if you are actually, let me take a point a little bit here, more x is here. We are saying that from this point, if you want this distance, this is the distance of x from the decision boundary. This is given by the result that we had. Distance of a point from the decision boundary is a beta naught plus a beta hat dot x. Isn't it? The distance function. And if you understand that, we have gone most of the journey in now formulating this problem as this river problem, flowing the widest river through the data. Let us say that, let me bring back your yellow points, a few yellow points, and a green point here. Where's my green point? Hang on, let me get rid of this. The green point here, right? So suppose we flow a river through this. This is our decision boundary. Are we together? Now you ask this question, this vector, or this vector, or this vector, you realize that they are at the same distance from the median. Right? So each of the points, vectors on the banks is the same distance. Let's say m. Let me call this distance m. Would you agree that all of them would be the same distance m from the decision boundary? Right? So this is your boat, right? Reminds me of a Greek mythology in which you are between, what is it, a rock and a hard place. It used to be Psyche or something like that. Anybody remembers the Greek mythology, those two monsters in the sea who were waiting to devour you and your ship, and you had to avoid.
Scylla and Charybdis.
That is right, thank you. So it's like that, you want to avoid both the banks, otherwise you'll capsize your boat. You want to go through that. So you'll be equidistant from both of them. So you agree that all this, so from this we derive that the support vectors, in the simple case, the margin, the points on the margin are given by d of x is equal to m. Are we together? This is very obvious, isn't it? Because this distance is, after all, d of x here, distance from the hyperplane. This looks obvious, isn't it, guys? Please tell me that it is.
Yeah.
It is.
Yes.
Let me say that the direction of this river, which direction that you're flowing it, is given again by an orthonormal vector, a beta hat. So our other constraint is beta hat size is equal to 1, which means that beta 1 square plus beta 2 square beta n square is equal to 1, right? This is our constraint number 2, right? And now let us be a little bit more clever. Let us say that we call these points the negative points. Houses are, you know, as a target variable, when you give it, you can say y is equal to -1. And here for trees, y is equal to +1, right? As a y -1 +1, why not 0, 1, why not just house and tree? You'll see it's a mathematical convenience. You'll see what it is, and you'll see it shortly. So you realize that for trees, for all tree points, let me mention this as a crucial observation, for all tree points, what would be the constraint? Dx, they will be at a positive distance. Let's say that this distance is positive, this distance is negative. Dx for a tree, for any tree point x tree, is greater than equal
Positive
to m,
M.
isn't it?
Positive M, yeah.
Yeah, and at the same time, distance of any house point is less than equal to m. Would you agree, guys? Right? They would be minus m, sorry, less
Minus
than
M.
equal
Yeah.
to minus.
Minus.
This crucial minus is important, right?
Yeah.
So now if I write xt as a x minus or x house as the positive distance, or we don't need to do that. Now, these are two different constraints, isn't it, guys? You would say that find me a river says that this constraint is fulfilled for tree points and for house points. It's like this. So there's a clever mathematical trick. If you multiply this with the y for tree, what is the y for tree? +1, right? Y tree dx tree. Let us multiply. Now this happens to be 1 + 1. And so this constraint will remain. If you multiply this equation with +1, it will remain this. On the other hand, y house is equal to -1. If you multiply it by dx house, multiplied by dx house, what happens? When you multiply an inequality with -1, what does it happen? What happens to it?
Reverses the inequality.
Yeah, the sign reverses. And so this will also become like this. Do you see this, guys? And so it's just a clever mathematical trick. It's just being clever with the symbols. And so you can write it as a simpler equation, which says that for all points in the data, you want to find that decision boundary such that irrespective of whether it is a house point or a tree point, this constraint is fulfilled. Do you realize that these two become exactly the same equation? Right? So this is our next constraint. Right? This is without penalties. Without penalties, right? So if I were to write it down, let us write all the three constraints. So summarizing, for, and I will use the word hard margin classifier. For that maximal margin, for maximal margin classifiers, when we don't allow for mistakes, when there is no allowance or budget for mistakes, right? And so we are talking about the hard margin. For hard margin classifiers, that is for the definition of hard margin classifier is these are those maximal margin classifiers where there's no allowance for mistake. The opposite of that is sidebar. Soft margin classifiers are, what can you guess about that?
There is some allowance.
Yes, soft margin classifiers. This is terrible. Let me write it in the next sentence. Classifiers budget forest. Yes, are the maximal margin classifiers. By the way, is my handwriting fairly legible, guys, when you later on review
Yeah.
classifier, where the budget C for mistakes is greater than zero.
Zero.
Greater than zero, right? It's not zero, right? It is some value. It is some value that you set. Typically, the values could be 0.1, 0.01, 1, so forth. A certain amount of, typically you do it in powers of 10, this budget. So we are talking about hard margin. For hard margin, classifier, we realize that our constraints are that yi, distance xi, is greater than equal to m, some m, isn't it, guys? At the same time, you also say that the beta vector, beta hat, the unit vector, is equal to 1 because that goes into the definition of D. In other words, i.e. beta 1 square plus beta 2 square, beta n square is equal to 1, right? This is the second constraint, right? Let me just say equation 1. This is equation 2. Are we together? So any kind of river that you flow where these, and by definition, as we saw, dx is equal to beta naught plus beta 1 x1 plus beta n xn, right? So I'm just trying to map it to the notation of your book. Right? And so you could rewrite this whole constraint equation as saying that this thing therefore can be written as yi dxi can be written as greater than m is the same as writing yi beta naught plus beta 1 x1 plus all the way to beta n xn is greater than equal to m, right? This is obvious, isn't it, guys? It just comes from the definition of this. So in your textbook, actually, I've mapped it now, this intuition, to your textbook. So your textbook, this is, by the way, chapter 9 of your textbook. The reason I mapped it to that notation so that it becomes easy for you to go and review the stuff. Actually, this derivation is not mentioned there. And it is my sort of a crazy way of deriving it or looking at it from a more intuitive perspective. But I hope that once you have understood it, you can read more formal books and get the intuition. So this thing, you find innumerable videos on support vector machines and on maximal margin classifiers and so forth. They all talk of the orthonormal, and they sort of go a little bit fast because I suppose this is understood usually by people who really care about it and they have a lot more mathematical training sometimes. But I thought I will go through the entire derivation for you here. Now comes the next question, the soft margin classifier. By the way, can I ask you guys one thing? It's 9:15. In 15 minutes, it would be 9:30. Can I take some more time today? We started a bit late. Is that okay with all of you? Can we stretch?
Okay. I'm fine till 10 at least.
Yes.
10, so 10 is a hard constraint. All right, let me try to respect that. So
I'll have to drop off at 9:30.
Okay. So now the only difference is yi, you remember the times the distance from the decision boundary must be greater than equal to m, but in some cases, for some points, you allow mistakes. Are we together? So for every data point, you have a certain penalty factor. You hope that most of the penalty factors are 0 and some of them are non-zero. Are we together? But for those terms, you allow a decision boundary smaller than m. In other words, suppose there is a river here. This is a point, this is a point, this is a point. This is M. You allow for this point. This is less than M distance. Let me call this mistake Q. You would agree that let Q be a mistake point, isn't it? A mistake point. Then for Q, you would agree that Q is the Q point. Distance of Q is less than M, isn't it? It is not as far. This is M. This is some small distance, a distance that is less than M. So that is why M minus some amount, right? So you define whatever it is, the epsilon Q is M minus dQ. This is the mistake that this guy made. Do you see that, guys? How much penalty or how severe is the mistake is based on this. So far, so good, guys?
Can you please repeat how you wrote this one? EQ is equal to 1.
So the Q, this point is Q, let us say.
Yes.
So the distance of Q from this line, whatever it is not as much as the distance of the river banks from the center, from the decision boundary, isn't it? So
Yes.
whatever dQ is, it is less than M, right? And how much is the mistake there is? A Q should have been here. It is instead here. It should have been ideally here, but it is here. So this is the mistake EQ that or the penalty that you're allowing for, the softness that you're allowing for.
Got it. Thank you.
And that's what I'm saying here. And so that is essentially the point that we are making here. And so you allow for some mistakes. And then the rest of the equation, so again, to come back to it, what are the basic rules? You want to say that for all points, dxi is greater than equal to M, up to some tiny mistakes that each of the points can make. Most points should make no mistakes, some point can make. But then there is also the constraint, the summation of all the epsilon. Actually, let me use the full other epsilon symbol so it doesn't look like summation symbol. The sum of all the mistakes should be less than equal to a constraint, isn't it, guys? This is true. And finally, the one obvious statement is beta hat is equal to 1, i.e. beta 1 square plus beta 2 square plus beta 3 square beta n square is equal to 1, right? So these three, so your root is that this is just a small adaptation over the hard margin classifier. This is it. So these are, so what you're saying is give me a decision boundary that respects these. In the hard margin classifier, you're saying, give me a decision boundary that respects this by definition. Where are we? Okay, that respects this, right? Now the machine learning algorithm has to just go creep over the feature space using some clever means and gradually flow to find the best river that it can flow, which respects those conditions for those two different algorithms. Are we together? So now we took care of mistakes. And that soft margin classifier, is it effective? Very effective, guys. But there is yet another problem with rivers and our model. While for the simple case it works, in real life, rivers tend not to run straight, do they?
No.
Right? Rivers tend to meander, right? So let's use that intuition. Now, let us say, but rivers meander, they will. Like this, right? More formally, oftentimes, the decision boundary is nonlinear, is a nonlinear surface, hypersurface, is it? Isn't it? I'm using fancy language, but I hope, guys, whenever you understand things, remember that if you bring intuition to mathematics, you'll realize that all of mathematics, and certainly all of machine learning, is saying something very obvious. Right? We're just writing it more precisely, the obvious statements more precisely. That's why I always say that math is the easiest subject in the world. Coding is much harder than math. Everything, I have spent my life, as you know, I went through IIT engineering, electronics engineering, and I did theoretical physics, mathematical physics. So I did a lot of math and a lot of physics, did computer science, right? And all of that, hardware, software, everything. From my experience, I've never found a subject so absolutely obvious and easy as mathematics. The trouble with mathematics is, how do you see it the right way? So one picture that somebody, in the social media, people keep forwarding pictures. One recent picture somebody forwarded, I don't know who, very interesting. It just showed that there was a picture of a big stone that mysteriously was floating in the air, big rock. It was floating in the air. And the thing is, you're puzzled. What is going on? Why is it not falling to the ground? It just is levitating on its way. And you stay puzzled for quite some time till you invert the picture. And when you invert the picture, you realize that, well, actually the picture is in the water. The rock is in the water. And what you thought of as sky was actually the water, and what you thought of as the ground was actually the sky, and so on and so forth. So a lot depends on perspective. And mathematics is always, all of machine learning theory, guys, boils down to, if I may say so, and go on a tangent for a moment, it is all the search for that perspective which makes the problem look trivial. In mathematics, that's why mathematicians often will say statements like that. This and then this, and from this we prove this, and from that, as you can see, this happens, and therefore it becomes trivial. So when they use the word trivial, they mean it. What it meant was not trivial in a derogatory sense, but they, through a chain of reasoning, they made the problem equivalent to something that is self-evident, right? And that is the pursuit of machine learning. When you do that, think of it like that every algorithm, you have to look at it in a way that makes it look obvious. Support vector machines are notoriously hard for people to understand. Most people, in fact, do not understand support vector machines. You can try it. If you have data scientists in your workplace, walk up to one of them and say, explain to me support vector machines. Explain how they work, explain the theory of it, and you'll get blank stare. Quite often, one or two geniuses might be around, but people find it hard. But in my view, it is hard because you don't look at it in an intuitive way. And always try to relate things to stories. Like, for example, this river metaphor that I am using to carry this learning forward, use something like that from your real life. It helps. Yeah? Then it becomes very real and easy to get the intuition of. So we'll do that. So suppose you have a nonlinear decision boundary. What do we bring to our rescue? We bring something that we learned in ML100. Remember, we learned that we recall that every curve can be linearized in some higher dimensional space. So I have a silly analogy, since I'm giving so many analogies. You know, even the most wicked person is absolutely perfect in the eyes of his or her mother. Isn't it? I'm pretty sure that Hitler's mother must have been very fond of him, and so forth. And you can think of all sorts of villains in history. But in the eyes of the mother, the child is always perfect. So I always say, in a very silly analogy, that every curve, and therefore is generalization, a hypersurface, there exists a higher dimensional mother space in which that curve becomes linear. And I'll sort of illustrate it with an example that you have seen. So suppose you have a parabolic curve like this, right? So this is you can write it as an equation as some beta naught plus beta 1 x plus beta 2 x squared, right? There is one bend in this curve, so you realize that maybe a quadratic equation would be good enough. right? And your high school algebra tells that indeed it should suffice if it is truly a parabolic thing. Now, this is two-dimensional, right? This is R2. How do I linearize this in codes? You go to a new space, which is three-dimensional, right? So this is y, x, which is three-dimensional, in which the axes are x, and this axis, let me just call it x1 is equal to x, x2 is equal to the square of x, and the third dimension is y. And you will realize that if I write it as in that form, this equation becomes y is equal to beta naught plus beta 1 x1 plus the beta 2 x2, isn't it? In R3, and this is a linear equation. This is an equation it's as trivial as that. It's a linear equation, a hyperplane, in fact, it's a plane. It's not even hyper, but I'll use the word a plane. It's a plane. I meant to put the word hyper here, but here. Actually, let me just leave the word plane. It's a plane. It's a plane. It is a plane. A plane is flat, isn't it? It's some plane. I don't know. Some plane here. It's an equation of a plane in a higher dimensional space, which is three-dimensional space. And this intuition carries forward. There are two kinds of curves that can be represented with a finite dimensional polynomial, and curves that cannot be represented by finite dimensional polynomial. So they will need an infinite dimensional polynomial space. But polynomials are not the only basis functions. You can use sin x, the Gaussians and so forth. These are the things you will learn in the engineering math class that is coming up. So we won't go into it, but just to give you an intuition that you can build your axes out of any kind of functions and then expand or write your curve, or imagine that your curve or your surface, your decision boundary, is a finite dimensional expression in that basis function. You can get away with it. Or sometimes you literally want infinite dimensional spaces. So you can take your data, and this is hard to imagine. How do I draw a line in an infinite dimensional space? It seems rather impractical. There is no pencil that will help you do that, of course. But in mathematicians tend to generalize with abandon and say, well, I can still imagine that. So we'll do that. Imagine a high dimension space. So now what has that to do with this? Well, the statement is very simple. Since any curved decision boundary, well, let me use the more formal term, non-linear. What is non-linear is therefore curved, right? What is this? Non-linear, or in simple terms, curved decision boundary, any nonlinear decision boundary is straight in some higher dimensional space, or let me call it D, which is a high dimension space. Now, think of the river. So what it means is that our meandering river, this river that sort of goes like this in R2 becomes what? It becomes a nice, simple, straight river. Do you see that, guys? Huh? It becomes a straight river in some higher dimensional space. And so if that is true, then all we need to do is go to that higher dimension and use everything that we just used, the maximal margin classifier technology, find the support vectors and come back. Am I making sense, guys? You're getting the intuition. Eh? So if in some higher dimensional space, the river is truly straight, then all I have to do is have a magic manner to go to that higher dimensional space and then solve the problem there, just the way we learned to solve the problem. This two-step process, right? A, two steps. A, go to a linear high dimension space. B, then bring back your maximal margin classifiers. Classifier. These two together is essentially the gist of the algorithm support vector machines. Right? This together is the support, the algorithm support vector machines. But it leaves a fundamental problem unanswered. How in the world do we discover this space? A given data set, isn't it? So it is very easy to say that go to that other mother space in higher dimension where the river straightens out. But how do you get there? How do you discover that space? That problem remains there, right? Do you guys understand the situation?
Yeah.
Right? So the answer to that is actually very, very elegant. And it is in fact the last insight that Vladimir Vapnik got. So I will state it for you in simple terms. I'll just sort of give you the intuition. What it says is that a lot of problems in machine learning can be formulated as dot products, right? Dot products. This dot product, A dot B, right? So imagine that there is a vector. You remember that a vector is invariant of what reference frame you look at, right? And if you have 2 points, how close they are is given by A dot B. Right. Now, it turns out that the nearness is preserved as you go to higher dimensions. Close points remain close. Right. Now, I won't go into the full mathematical specification, but I will just say that a point can be defined using its dot product with its neighbors. So if I say that there are these 3 points and the dot product with 1 and 2 and 3 I give you, you would have no choice but to place the point here because you have written a set of equations of dot products of that x dot A is equal to something, x dot B is equal to something, x dot C is equal to something. When you solve for this equation, you will end up solving for x. So you can actually specify a lot of things, reformulate a lot of things in dot products. Now, why are dot products interesting? It is the so-called kernel trick. And I'll give you the intuition of it. What it basically says is that if you want to solve a problem, like find the decision boundary, and you can specify the decision boundary as a dot product, then you have to do a dot product in the higher dimensional space. So there are 2 steps involved. A, go to higher dimensional space. B, do the dot product. Right? And see, kernel of the dot product. Let's say kernel of the dot product. Kernel means any function of dot product is a kernel. Are we together, guys? Right? Kernel is the word that is reserved for that, functions of dot products. And now here comes the magic, kernel dot product. Come back with results. And the kernel trick is this. Sometimes you can do the dot product in the higher dimension without actually finding all the details of how to go from here to there. It's a very interesting trick. You know there's a higher dimensional space. In that higher dimensional space, you need the dot product. You can actually get the dot product and your functions of dot products without necessarily finding explicit mapping or translation rules from this space to that space. Right? Now that's a little bit mathsy. I'll give an extra session for it. It's beautiful math, actually. It's a very elegant math and some dual space and so forth. But we'll do that at some point, right? It's an extra session. It's certainly not beyond the scope of this class. And when you do engineering math, we will go through this carefully. And so the support vector machines became powerful And Vapnik realized that he had hit upon something when finally the last piece of the puzzle fell in place. And he realized that, well, every problem can be linearized. You can flow a river through the data. And what is more, the process of going to that linear, you don't need to solve the whole problem. You need to solve only a small part of the problem, so long as you deal with dot products. And thus the technology of support vector machines. Support vector machines is one of the simpler kernel machines, right? The scope of kernel machines is huge. Next time we will use kernels to do nearest neighbors. Kernel nearest neighbors. We'll talk about dimensionality reduction. Let's keep those things for next time, because I noticed that we are running out of time today. But this was, guys, the theory of support vector machines. Did you understand it, guys, or did you understand most of it? Anybody found it interesting?
Yes.
Yes, mostly got it.
Yes.
So Asif, this is Avijit. So just one point here there. So here, what is the kernel here? So kernel is basically sort of a function which translates from the lower space to higher space.
Kernel of, just think of some things that xi, xj, the dot product function, roughly speaking, they're functions of dot products.
Okay. But actually in an intuition form, it is basically helping translate those points in the lower dimension to higher dimension. They are functions, mathematical functions.
Kernels are mathematical functions that help you give something. For example, distance is
okay.
right?
Okay.
But the beautiful thing is, if you can formulate your problem as a kernel problem, then the translation rules from this to higher dimensions, which may be bizarrely complicated, you don't even need to worry about it. You can sort of get to the kernel faster than you can get to solving all the rules of translating from here to there.
Okay.
And that shortcut actually saves you a lot of computation and makes this whole thing very, very practical and relevant. See, the first time you see the kernel theory come together, it almost feels like magic. Wow, you can actually do that, right? And you can imagine the tremendous insight that is embedded here, and how Vapnik must have felt in 1960s. When he came up with this theory, he sat upon it for almost, 20, 25 years before it finally got recognition. But when it got recognition, people knew right off the bat that this is fundamental. This is a breakthrough. You know, the time for recognizing that algorithm had come. It had been discovered way ahead of its time. We use kernels everywhere, even in deep neural networks and everywhere. So we live in a world where kernels are taken for granted. We will delve into kernels much more in the audience at this moment. This is a practical methods workshop. So we won't delve more into the kernels, but certainly in the engineering math, the math behind data science class, this will be a hot topic. We'll do it in depth. And we'll do the whole derivation of it in depth.
When is that happening?
Asif, sorry.
That is something I want you guys to make a predictive model for. Predict the day.
Okay.
Now, I don't know. See, we are living in the COVID world. It's a new
It's an
world.
ensemble. You have to do an ensemble of all these people, voting machines.
You guys can all guess and see where the guess lands. If I have to guess, it'll be, see, it depends upon when I have enough people. Maybe I should open the registration and say we'll start when we have enough people.
Yeah, let people vote. Yeah.
Let me do it like that. It is actually, it's a surprising thing. One would think it's an abstract thing, but I think of all my courses, the boot camp and the math class, the math of data science are the most popular. They usually go houseful. Some of you have, how many, is there anybody who has attended my math class? The math of data science?
I have.
Yes. Yeah.
Asif.
Did you like it? Did you guys find it relevant to what we are doing and talking?
Yes, that is actually the ABC of machine learning.
Yes, it's the heart of it.
Yeah.
So Asif, here we are finding dot product and coming back. And what are we doing again? Like when we find the dot product?
See, I did a lot of hand-waving arguments. I hit a lot of mathematics. But what I'm basically saying is you can find the decision boundary using some clever mathematical tricks in higher dimension and solve your problem, right? Without actually knowing explicitly how you went from here to there.
Yeah. Can you scroll up a little bit here? Yeah. What?
Yeah, 1 second. Yes.
So here we are trying to find what A and B. Okay, so A is your this one. Okay,
Any
the
2
3
points.
points.
Suppose I take X and some reference point X and Xi. They will have a dot product, and any function of the dot product is called a kernel. Is roughly speaking, any symmetric, I mean, obviously dot products are symmetric, so any function of the dot product is considered a kernel. So in support vector machines, we typically use 3 kernels. One is the linear kernel. What is the linear kernel? The linear kernel is literally the dot product between xi, xj. The kernel is kernel xi, xj is quite literally the dot product. Right? I'm using this as the dot product, also written as xi dot xj, right? Like that, but because dot is sort of gets lost in writing, so I write it with this angular bracket. Then there is a polynomial kernel. The polynomial kernel is xi, xj is quite literally that, a polynomial of the dot product. You allow for the basic term also, xi, xj, to the power d, some power, polynomial power d, right? And then there is a more powerful and quite ubiquitously used kernel. It is called the Rbf kernel, Rbf. Now, what in the world is that cryptic word? Radial basis functions. Yeah, well, that too is cryptic. What is that? It is basically a bunch of Gaussians. Or think of it as bell curves in higher dimension, right? Gaussians, Gaussians. A lot of, you can write it as a bunch of Gaussians. So your kernel would be written as the kernel xi, xj is equal to e to the minus gamma. This is a suppression, considered a suppression factor. Xi dot xj, right? I believe square. Right? There's a square, and you can put a d2 or something like that. The typical Gaussian, the 2 factor divide by 2 is subsumed in this gamma. It's a suppression factor. What it means is if you plot this e to the I, you will realize that it can, if it is gamma is small, it will be like this. It will be stronger and stronger gamma will suppress it. You see that this curve is being suppressed down as gamma increases. What is gamma? By the way, this is a Greek symbol gamma. Gamma, right? And so what is the intuition behind it? The intuition, the way I would suggest think of the intuition is, see, a polynomial is simple. I showed you that a curve can become straightened in a polynomially high space, right? A polynomial of degree 3, for example, 3-dimensional, 4-dimensional space, and so forth. That is the polynomial kernel. The radial basis function kernel is interesting. It's sort of an infinite dimensional kernel of sorts. You take there, but yeah, so we'll come to that. Let me not go to that. What it basically means is that, suppose you have a complicated river. Let me make this river like this and like this. Remember that these points are like lighthouses shining. So if you can find lighthouses, enough lighthouses, support vectors, right? Enough lighthouses shining. And maybe a couple of mistakes in here, which are, by the way, those mistakes are also called support vectors because they help support the decision boundary. You realize that you can draw your, you can navigate this river using these lighthouses. Isn't it? All you need is lighthouses along your path. Does this make sense, guys? Am I?
Yes.
Oh, sorry. This yellow thing should stay. as a boatsman, you just need that the river bank should be lit, right? The metaphor is you just want, as a boatsman, just want the river banks and mistakes to be lit with LIT, it should be lit with enough lighthouses along the way. Is this intuition obvious, guys? Isn't it? As a boatsman, at night, you just want the river banks and the mistakes to be lit with enough lighthouses along the way. If it is, you can navigate your path, isn't it? And support vector machines is just a means to find these lighthouses. Support vector machines, M, is an algorithm that cleverly finds these lighthouses for you. Of course, needless to say, these lighthouses, more formally, these lighthouses are called support vectors. Well, I hope that this workshop series in my little training place truly represents lighthouses or support vectors to guide you guys along your learning journey. And
Yes,
that's the name, yes, and that's the name of my company. With that, we'll stop, guys. I'll take questions for the next.
Sir, I have a question. So if say the width of river is, say the river is narrow, right? In that case, that also means that the classes are overlapping. So
Yeah, you allow for mistakes, Pradeep. Because you allow for mistakes, it may be true that a river may have washed to the other bank, right? Or one of these boat houses is sitting on the bank of the agricultural side. Because you allow for mistakes in between, the overlapping regions are the mistakes, isn't it? You can still flow a reasonable river through it so long as you have a good budget. Budget for
even though it is, it depends on individuals to decide how much budget they want.
Yes, or more formally, see, ultimately the proof of the pudding is in the eating. When you're building a support vector machine classifier, let us say, how do you choose the budget? You choose that budget which gives you best accuracy or performance on the test method, isn't it?
So if say it is binary problem, sir, and
let me finish that. So sorry to interrupt you. So in other words, that budget is a hyperparameter of the model, isn't it? So in a support vector machine, there are two so for example, budget is one hyperparameter. Let me just write it down, parameter, so that is part of the notes. Hyperparameters are C, the budget. Actually, most people don't call it the budget, they call it the cost, which I find non-intuitive. In the literature, you will see that the way scikit-learn and your textbooks call it, they call it the cost. Actually, it's the opposite, is the budget for mistakes. And the other is, each of these, for gamma is the gamma for Rbf, dimension, degree of the polynomial for poly. In polynomial kernel, you still need to decide what your D is, right? What's your optimal D is, and it will figure it out. You can tell it to just go figure it out. It will do that. and so forth. So you have certain degree of, actually, I would say that these days the libraries just do figure it out on their own. But there are certain hyperparameters built in. Typically, you use Rbf quite often if your problem is complex. So these two become at least two of the hyperparameters in the model. Go ahead, Pradeep.
Okay, so for the non-linear problems, like where the river is not straight, the Rbf can help finding the lighthouses.
Either the polynomial or the Rbf. See, remember, linear is out of the window, isn't it?
Right.
So you'll have to try polynomial or Rbf, one of the two.
And so if it is binary classification problem,
yes.
So in that case, I'm just wondering whether linear regression will be more efficient just for the accuracy point of view.
Remember, linear logistic regression draws a straight decision boundary in the feature space. So you would get screwed. Your river is nonlinear. Decision boundary is nonlinear. So it won't work. No? So the burden to go to higher dimensional space to linearize the problem is on you. And remember, we have been doing this. If you go back to your data set 2 for regression, what did we do? It was a sine wave-like structure. We went ourselves to polynomial degree. In the language of support vector machines, you would say that you have used a polynomial kernel.
River
And
data
then, do that. So let me say it one more way. See, you realize that finding a linear decision boundary is solving a linear problem. So all of machine learning problems ultimately go through two phases, whether it is support vector machines or it is deep neural networks or so forth. The first phase is somehow to linearize the problem. All of these things, the deep neural nets, and in many ways, they're clever ways, roughly speaking, they're clever ways to linearize a problem, to find that representation space in which the problem is linear. And then solving a linear problem is easy. So those of you who have played with neural networks, remember, what is the last layer of a neural net? It is just a simple linear regressor node, right? Activation function. One simple, or it is just a logistic function or a softmax function. It's a generalization of logistic. Both of those are linear classifiers. So what happened? You solved a whole big complex nonlinear problem by taking the input and adjusting the weights of the layers of the neural network in such a way that it found the true representation such that the problem becomes linear. And then in the last stage, you solve the linear problem. This is pretty much the way complex problems are solved. You find ways. You can do feature engineering, as we did last week. You can use clever tricks. You can use these powerful algorithms. They all just help you linearize the problem. Once your problem is linearized, then you use a last step is a linear algorithm to solve it.
Thank you, sir. Can you again explain a little bit about Rbf, sir? How the Rbf functions as a function? How does it work?
Pradeep, I would love to. That's a little bit outside the scope. Why don't we do it? Either let's do an extra session or do it in the engineering math, because it can be a bit intimidating. In the audience, there are a lot of people who want to delve on, stay with the practical side. For them, that math can be a bit overwhelming. That's why I sort of glossed over at the last stage some of the kernel level math, also for that reason. It is there, we will learn it, but we'll learn it in the other workshop, carefully.
Thank you, sir.
Asif, I know in this one, like in support vector, we don't have to find that higher order space, and we just did this trick, right? Dot products.
Yes.
But so why didn't we play the same trick in earlier problems? Why we have to find polynomials in our other algorithms?
Right? So we are learning. So what happens is that, see, when we can do by hand, it's the gold standard. It's an open model.
I see.
Support vector machines are black box models, right? So it is very difficult for you to find out what is the space that this machine discovered.
Yeah, but there's no need.
Interpretability is a huge casualty here, right? At the end of the day, support vectors is still remarkably interpretable, because through the data set, what did it do? It says, don't tell me how, but I discovered these lighthouses.
Yes.
And once you know the lighthouses, the support vectors, you can literally see the intuition. You can see how the support vector machine is making its decisions. It becomes evident. So in that sense, it remains interpretable. But you lose this fact that how in the world did you pick these as the lighthouses? Yeah. What was the reasoning behind it? And then it says, well, welcome to the land of mathematics, and let's talk constraint optimizations and dual spaces. Your business guy will run away.
But you still get that function at the end, right? Because you got those lighthouses.
Yeah, exactly. That's that. So it's all beautiful math. We'll cover it, guys, at some point. But okay, we have 3 minutes left. As somebody said, 10 is a hard cutoff. Any other questions? Was it fun, guys? I find support vector machines to be one of the most beautiful gems in machine learning.
Yes, sir. Sir, small.
Yes.
So even if we, after a limit, and then it will gonna start overfitting, right? Doesn't matter. We cannot increase the budget unlimited. So it will gonna start overfitting then, right?
No. What happens is if your budget is too small, it starts overfitting because it tries to find the narrowest river that may still exist, or it may not find it at all.
Okay.
But if you make your budget too relaxed, you have bias wide error. So imagine that your budget is very wide, right? Big. So what will happen? A huge river will come up. No? That is basically flooding the houses and the trees.
Got it. Yeah.
As you can make out. And there'll be so many mistakes, bias errors, isn't it? It's a simple, more or less straight, simple river, hugely wide, flowing through it. So a large budget leads to bias errors. A small budget leads to variance errors. That's sort of the bias variance trade-off in this situation.
Thank you, sir.
Yeah.
Asif,
Go ahead.
I think just one thing that helps me is the way to visualize his functions is, after all, also a vector. It's like infinite number of vectors connected.
Exactly. Functions are vectors.
And once it's vector, then you do linear transformation and preserve the distance between the dimensions, right?
Right. And that's what I meant when I said radial basis function. They are basis unit vectors in an infinite dimensional space whose axes are these bell curves, these basis functions. But that's getting a little mathsy. Let's do it in the relevant workshop. All right, guys, I hope you enjoyed it. In the end, I did gloss over some of the higher level mathematics for a reason, guys. From a practical perspective, you need to know the intuition. And I hope today you learned the main intuition. It's a beautifully argued thing. And to think that one man in one Russian winter sat down and thought through it is just amazing. And it turns out that he was not the only one. There were other people who were thinking along similar ideas a few years later and so forth. Today, when you look at the support vectors theory, you see a reference to a lot of researchers. But at least one of them, and in fact, he's considered the leading light on the topic, he did discover, or independently, and perhaps before other people, a lot of this years and years ago. Quite remarkable, isn't it? All right, so with those words, I'll stop the recording and I'll let you guys go. If you want to stay back for something, you're welcome to, but I'll stop.